All right. Hey, everyone. This video is going to cover the nuclear decay notes. As I promised in some of the classes, I will go over the equations, how to make the nuclear decay equations, but I'm also going to cover the why this occurs information because we didn't get to that in some of the classes. So the why, what is it behind nuclear decay that allows it to occur? Okay, so radioactivity or radiation is spontaneous. That means it just kind of happens on its own. Emission, that's giving off, of radiation from the nucleus of an atom. So the first thing we have to sort of think about is what's going on inside the atom. Well, if you look at the FET stuff that you guys played around with the other day, we've got in the atom, there's protons, neutrons, and electrons. Electrons are not in the nucleus. They're outside in the electron cloud. The protons and neutrons are in the nucleus. So if you recall, neutrons are neutral, protons are positively charged. What this means is the only charge, the nucleus itself is positively charged. Okay, and if you recall from the information on discovering the atomic structure, we know that like charges or the same charges will repel each other and opposite charges attract. So if all we have are positive charges inside the nucleus, you would think that those positive charges would be repelling each other, which they are. However, we also have strong nuclear force and a weak nuclear force. They're both attractive forces, and they act between all subatomic particles, protons and neutrons within the nucleus. The strong nuclear force is what holds the nucleus together against the repulsion force created between the protons. So imagine you have two really powerful magnets and they're repelling each other because you've got the same poles going to each other. But if you're anything like me, sometimes you want to just screw around and you want to like mash those together. You want to see if you're stronger than the magnetic force, right? So you grab the magnets and you smash them together and you hold them even though the magnet's repelling away. That's sort of like the strong nuclear force. You're acting like the strong nuclear force there. The magnets are still repelling, just your force that you're putting on them are stronger than that, so it's holding them together. Okay, so the protons are repelling, but the strong nuclear force that's acting among all the different particles is holding everything together. Okay, so basically what happens is because the strong nuclear force acts between protons and neutrons, protons and protons, neutrons and neutrons, it overwhelms the repulsion force because the repulsion is just between the protons. Okay, now, what happens when, so as hopefully you noticed when you were using the FET, what happens when we take away some neutrons? It becomes unstable, right? That's because the strong nuclear force is struggling. It's having a really hard time holding it together against the repulsive forces. You might have also noticed if you added too many, so it becomes stable. If you add too many neutrons, it becomes unstable. This is because the strong nuclear force also acts like a magnet. And if you think about magnets, the attraction and repulsion, the further apart from each other they get, the weaker that push or pull is. So the bigger, like when you're adding more neutrons, you think, oh, it becomes more stable because you're getting more attractive forces and they're not repelling more. Well, that's true, but the problem is that also makes the whole thing bigger, and it causes those to spread out, so it can make that more unstable. Okay. So, all right. So what happens, actually, I guess I should leave this up. So what happens is when this becomes unstable, okay, it's having a hard time holding everything together. So you have your so you have your original your original nucleus. Okay. When it becomes unstable, the strong nuclear force can't hold it together. If it becomes unstable enough, the original nucleus splits, and part of the nucleus literally like tears off, chunks off, and goes on its own way. So what you get is you get whatever's left behind the new nucleus, which is a new element, and you get the chunk that broke off, which in the first case that we're going to talk about is the alpha particle. Okay. So the important thing to remember with this is that you had one thing and it broke into two parts. So if you were to add these two things together, it would take you back to the original nucleus. Okay, the law of conservation of matter says matter can't be created or destroyed. It has to come from somewhere and go to somewhere. So in a way, people see this somewhat as destroying matter, but it's at a subatomic level, it's not. They're both still there. It's one of them left, sort of. Broke off and left. Okay. So what happens then is when when part of the nucleus breaks off and leaves, it becomes more stable. The new nucleus is now more stable because some of those, so the alpha particle, I guess I should mention, the alpha particle is 2 protons and 2 neutrons. Okay, that's in your notes. So because some of the protons are leaving, so some of those repulsive forces are leaving, so this kind of calms down then. And so this is sort of the why behind radioactive decay. The nucleus is unstable because of the repulsive forces, and until part of that nucleus like rips off or tears off, it would be unstable. Once it does, that because it's taking away some of the repulsive forces in the protons, it calms down the nucleus. And then that new nucleus is more stable. Or it'll keep having decay. If this isn't stable, it'll keep having decay until it becomes stable. Okay. All right. So your strong and weak nuclear forces are the attractive forces inside the nucleus that help hold it together. Now, how does radioactive decay work? Well, we've got some different types. The one I was just talking about is alpha. Okay, this is now these are written just like a chemical symbol that we worked on last week. Okay, so remember the top is the mass number, which is protons plus neutrons. The bottom is the atomic number, or the number of protons. This is an alpha symbol. Okay, you'll see me if I write them, it looks kind of like a fish. That's from the text there, but like if I were writing the alpha particle, it would look like this: 4, 2, and then kind of like that. Okay. So alpha particle, sometimes you'll see it written like this because if we look here, helium, what is helium? Well, 2 protons, 2 neutrons, 2 electrons. So look at the symbol here, 4/2He. 2 protons, 2 neutrons. That's essentially an alpha particle. Now you'll see it written like this. I feel that's a little misleading because an alpha particle, like you'll see an alpha particle written like that sometimes, it's 2 protons and 2 neutrons, but not 2 electrons. So that's why I put it like this, which is just 2 protons, 2 neutrons um, without the electrons. I want you to write it like this, the first one, the 4/2 alpha. If you see these, just know that that's what it could be referring to. That basically an alpha particle is a helium nucleus. Okay. All right. How does the equation work? Well, the way the equation works is it's just like an algebra equation. Okay. The arrow is the equals. This is before the decay. This is after the decay. So remember, before you have one thing and it busts apart into two things, right? Before, after. Arrow is like the equal. So look at the numbers like a math equation. 133 equals 4 plus what number? Well, 129 plus 4 is 133. Okay, down here. 55 equals 2 plus what number? Well, 53 plus 2 is going to give you 55. Okay, you can do it like if you're thinking of it mathematically, like if we had, move this out of the way here real quick. Okay, you've got 133, right, equals 4 plus x. You'd be technically subtracting 4 from both sides, right? So you'd get like that. And then the 55 is the same, it's the same type of thing. 55 equals 2 plus x. So subtract 2 from both sides, you get those. So your final, what you have for your second part of this is 129 on the top, 53 on the bottom. How do you get the I? Well, to get the I, you're going to go to your periodic table. Remember, the bottom number, the number you found down here, the 53, is the number of protons or the atomic number. So you go to your periodic table, you find the thing with the atomic number 53, that's the top numbers on these, 53, it's iodine, so that tells you what the symbol is. All right. Okay, let's try one from the homework. So I'm going to do this first one here, number 1. These are all, the top 5 are all alpha decay. I have to tell you which one, type of decay I want you to do. So alpha decay. So you can rewrite it, or you can just leave this as your beginning thing. This is the beginning nucleus. Okay, so I draw my arrow. So what is it going to turn into? Well, it's alpha decay. So I have to have an alpha particle is one of my two things. So 4/2 alpha, plus we're going to separate the alpha particle from the new part. Okay, so we're going to think of it as 281 equals 4 plus what number? So, or 281 minus 4, so that's going to give us 277. 110 equals 2 plus what number? Or 110 minus 2 is 108. And we've got 108, so we're going to look up the thing that's with 108. 108 is here, so that's hesium, HS. That's our symbol. Okay, and that's the answer. That whole entire thing is the answer. That's the decay equation. All right. Okay. Let's take a look at the beta. Beta radiation. Beta radiation is radiation consisting of high-speed electrons. This is how beta radiation works. A neutron busts up into an electron and a proton. The proton stays behind in the nucleus. The electron leaves. So since the only thing leaving the nucleus is the electron, beta radiation is a stream of high-speed electrons. Okay, how do you write a beta particle? It's 0 over -1 beta. This is a beta symbol. It's like a capital B with a tail, and you have to have the tail. Because if you don't have the tail, then essentially you're talking about boron, which is something totally different. okay? Sometimes you'll see it written as 0 over -1e. I want you to write it like the first one. All right, these equations, it works the same way as the alpha equations, though, just like an algebra equation. So I use the same element just to show you. 133 over 55 CS. Okay, we got 0 over -1 beta is our beta particle, plus, so 133 equals 0 plus what number? Well, it's the same, 133. Okay. Now, here's this part can be tricky. 55 equals -1 plus what number? So if you're subtracting, you've got to remember it's like 55 minus a -1, which is 56. And if you look back, it makes sense. 56 minus 1 gives you 55. Okay, so also if you think about this over here, remember, how do we get our mass number? Protons plus neutrons. Okay, so we start out 133. What happened? Well, we lost a neutron because a neutron busted up. So we lost a neutron. So that takes us down to 132. But we gained a proton, so that takes us back up to 133. So our mass doesn't change. That makes sense. All right. What about our bottom number? Well, this is the atomic number, which is also the number of protons. Well, what happened? We gained a proton, right? Because the neutron broke up. So we gained a proton. So 55 to 56. That makes sense. All right. So let's do a beta radiation problem. Okay, on our homework, first 5, the alphas. Starting with 6, we've got a beta. So these are all beta ones. Okay, same type of thing. I'm gonna zoom in here a second. Okay. So I'm gonna leave this. And then we've got arrow, and these are beta decay. So it's 0, -1, beta, plus, picture plus, you're separating them. Now, let's see what we have. 243 is 0, it stays 243. On the bottom, 95 minus -1 means we add 1, so it becomes 96. We look up 96 on our periodic table, and we find Cm. There we go. That's the beta decay equation. So, yes, all of the alpha decays are going to start out the same. It's going to be the arrow 4 over 2 alpha plus, and then you figure out that second thing that's left behind. So all these arrow 4 over 2 alpha, arrow like that. Beta, same thing. These are all arrow 0 over -1 beta plus, 0 over -1 beta plus, and then this last part is what changes. Okay, now, do you need to write out the whole equation? Yes, because you're writing out the equation, not just finding the residual nucleus. So yeah, you need to write it all out. All right. Okay, last thing on this is gamma. Gamma radiation is a stream of high energy, non-particle electromagnetic radiation similar to X-rays. The reason I highlighted non-particle is because that's the key to why we don't, if you see, we don't have a decay equation here. That's because gamma doesn't have any particles. So there's nothing to actually like break off or subtract in gamma radiation. It's just energy. So, and that's also why gamma radiation is written as 0 over 0, because there's no neutrons, no mass, no protons, and then that's a gamma symbol. Okay, so there's no equation for that, but you should know that that's a third type of radiation. Right? Now, the stuff on the back here, don't worry about this for now. If we need it, I'll do it either later in class or I'll do another video at some other time. All right. Good luck. Hope it goes well.